Now we're going to talk a little bit about the science of wicking. Wicking is really the fluid transfer by means of capillary action. I like to think about it like a paper towel absorbing a spill on your counter or floor, or the process of putting a celery stick in a jar of fluid. In either example, the liquid rises up the celery stick or paper towel. If the object is seated within a colored solution, it would even turn a different color. That fluid transfer is happening through capillary action. That's another way to think about wicking. It's the transfer of fluid from one point to another. Fluid flow is governed by physical forces and properties. The primary force is surface energy. The surface energy is a representation of the energy between the fluid and the substrate and the capillary forces that are acting on it to create this new surface. The first step to wicking is in understanding what type of fluid you're working with. Are you trying to wick an aqueous solution, for example, or a water-based solution? A contact angle, as you'll see in the diagram, is formed when a drop of liquid is placed on a material surface. The drop forms a dome shape on the surface. The contact angle describes the wettability of a solid by a liquid. This is primarily used for water-based solutions or hydrophilic surfaces. In these types of environments, the water will be wicked, and typically the contact angle is less than 90 degrees. On a hydrophobic surface, by contrast, this can be characterized with a contact angle of greater than 90 degrees. As you can see in the diagram, a hydrophobic surface will repel the water, causing the droplet to swell on its surface, whereas on the hydrophilic surface, this will freely accept the aqueous solution at a rate determined by the contact angle. There are analytical instruments you can use to measure the contact angle when comparing it to various substrates or material surfaces. In addition to the contact angle, there are other methods that are even better for determining wettability with solutions like solvents or oils. To determine this, one must dive deeper into the surface energy of a liquid and material surface. In general, there are cohesive and adhesive forces that are acting on the droplet. In the diagram, you'll see cohesive forces that are trying to keep the droplet together, while adhesive forces are trying to get it to stick to the material surface or wet out. When adhesive forces are greater than the cohesive forces, wetting will occur. For example, if polyethylene, a common polymer, has a surface energy of 35, and if you have a water droplet that has a surface energy of 72, the water will not wet out. However, if this is a droplet of alcohol, which has a surface energy of 24, this is less than the surface energy of PE, which is 35. The result is that it will wet into the polyethylene because the adhesive forces are greater than the cohesive forces. Surface energy is related to capillary force. These adhesive forces create capillary forces inside of the tube shown in the diagram. If you think of a straw, the diameter of the straw is going to govern the height at which that straw can wick liquid without any additional external forces. If you suck on the straw using your mouth, you're going to be able to get the fluid to come up the straw. Under these conditions, the size of the straw, or the diameter, is going to be directly related to the height at which the straw can carry the liquid. You can also relate that back to the pore structure of a porous component. The smaller the pore size, the higher you can wick, or the further you're going to be able to wick your fluid against the force of gravity. The adhesive forces that are driving the capillary action are essentially pulling the droplets up along the side of the tube. We can use surface treatments to impact these adhesive forces and change the capillary flow and other additives to the liquids. This formula is really describing capillary rise for a simple column, but there are other laws of physics that will govern microporous structures like bonded fiber and sintered particles. These laws include Darcy's law and Purcell's law, and they will add in other characteristics that are important to consider when looking at capillary flow in these types of structures. There are many different types of problems that can be solved by wicking. Primarily, you're transferring fluid from one location to another in order to accomplish something. Whether it's collecting a solution or a sample, or simply moving it away from something else, or it's so that it can be delivered to another point. But there's often a critical capability of transferring that fluid originally from one point to another. We'll discuss these in more detail in the next section on specific wicking applications. There are many things to consider when finding your perfect fluid flow, and some aspects are very application specific. Things like fluid type and therefore surface energy can be critical in determining wettability. determining the surface energy of a fluid and the media that's going to do the wicking, understanding the viscosity of the fluid itself, determining how this relates to the pore structure and how long or how many times your device will be used are all critical to designing your wicking component. For example, do you need the component to wick something one time, or does it need to wick a fluid in multiple directions? There are many available options for these types of situations, and our material science experts can help you find the right solution. Now, we're going to review some key applications and design considerations within the space of wicking. Lateral flow assays and sample collection are very common examples of utilizing capillary flow. A prime example would be urine wicks or pregnancy tests. In this case, you need to collect a sample of urine and move it from one point to another so that the urine can react with a reagent or some other chemical formulation that's applied to the wick to produce a line or indicator of whether the patient is pregnant or not. More recently, lateral flow has expanded into the area of blood collection to determine certain disease indications within cell-free DNA. When utilizing a saliva wick for at-home drugs of abuse testing, you similarly would want to collect a sample of saliva and move it from one point to another to do the testing. Understanding the amount of fluid that you need to collect is a key first step. Understanding how you want to indicate whether you've collected enough solution, especially when working with hard-to-collect samples, is also critical to designing an effective collection or sample component. Understanding the viscosity, sensitivity, and non-specific binding requirements, or any other requirements resulting from different interactions between the saliva and the test are critical questions to ask your engineer. There are many different materials, geometries, and assembly options, so it's important to gather a full picture of the device in order to determine the best material and solution for your component. Microsampling is another common application for a wick. Here you can see a patient collecting a sample of blood from their finger, and instead of an intravenous sample, they're taking a microsample from your finger, where maybe you need only 10, 20, 30, or even 40 microliters of blood, instead of milliliters of blood. In this case, a porous structure is a great place to capture that fluid for both storage and testing. The wick can provide a visual and a physical indicator of the sample collection and completeness. In this case, when designing a microsampling device, it's very important to understand what type of fluid you need to collect. This is so you understand whether you need a hydrophobic or hydrophilic material, or perhaps you need to modify the surface energy of your substrate or wick in a different way to take into consideration the fluid that it needs to collect. It's also important to note how much fluid it needs to collect, for example, 10, 50, or 100 microliters. Do you want it to hold a precise amount, or does it just need to hold enough? How fast do you need to collect the fluid? Are you going to be taking a sample from a patient finger, for example, where you want it to be as fast as possible? Or is it another environment where speed isn't that important? These are some common considerations for microsampling when designing a device that will collect and transport blood, for example, but you can also consider other fluids for other occasions and devices. Shifting gears slightly from diagnostics to medical devices, there are many examples of wicks within medical devices. We're going to highlight a few here today. The first one is a wick to protect a CO2 sensor and capnography device. As in many oxygen-driven or breath-driven medical devices, there is frequently a need to maintain moisture, especially if you're going to be delivering that air back into the human body. This is because you don't want to dry out the patient's mouth and lungs. Devices are very sensitive to a buildup of moisture or to any presence of moisture that could impact the sensor. This is whether it's an oxygen sensor or a CO2 sensor. In this case, you need a wick to be able to absorb and collect that liquid. Again, similar to microsampling, it's important to understand how much fluid it needs to hold, how rapidly you need to pull this liquid, and from which environment it's coming and going to. Another consideration when dealing with medical devices is if you want your wick to be a bacterial barrier as well. To allow it to collect solution but prevent bacteria from getting through into the device is critical for many applications.